Here we're looking at the molecular orbitals for carbon dioxide. We're using the pictorial method. Similar to the construction of molecular orbitals for beryllium dihydride, we have a linear molecule which has d infinite h symmetry. However, we should not work in an infinite point group. So instead, we're going to use d2h, which is the lowest orbital or lowest symmetry that we can use. Now, as you can see here, I've drawn out all of the possibilities for the s orbitals on the oxygens and the p orbitals for the oxygens. You can see I've represented oxygen as a red dot, carbon as a black dot. So these are all of the options for the arrangement of the orbitals. This particular one is the px orbital. So we can see here x is in that direction. These are also px, however the polarities are not in phase with each other. So now we simply need to match up the symmetry with our character table with our pictorial representation of it. So we will match up what these groups do with the irreducible representation over here. So let us start with the px with the shaded on top, the unshaded on the bottom. So we need to match that with the symmetries over here. So there's a few things that we can do. You can notice that some of these are symmetric about everything. Some of them are anti-symmetric about a C2 rotation in the Z direction. And we're going to use that to our advantage to figure out which representation is for this particular picture. So let's start. E doesn't help us out any because that's 1 all the way down. So let's instead look at, say, inversion. Inversion is nice because we can tell whether it's a U or for Ungerad or a G for Gerad, which is Gerad is symmetric about inversion, Ungerad is anti-symmetric about inversion, and that will eliminate half of the character table immediately. So if this was inverted, this would go here and that would go there, and that's anti-symmetric because it doesn't look the same as what we started with. So we know this is a Ungerad representation. Now let's look at a C2 rotation about the z-axis. That will rotate like this and flip those two, which is anti-symmetric because the dark would move, the shaded would move down and the positive would move up. So now we've eliminated it down to either B2U or B3U. Now we can look at a rotation about the y-axis, which would rotate this down there and this over to here, which would be also anti-symmetric because, again, we end up with something that looks different. It is flipped than what we started with. We can also look at the other operations to confirm our choice, but at this point we have eliminated it down to just one option, and so we could write down B3U for this. Let's go through a couple more operations. If we did a C2 in the X direction, that would rotate this way. It would flip this all over there, and that would go over there, and we'd be looking at the same object, and so that is symmetric. So again, we've just confirmed that this is a B3U representation. Now we just need to do that for the rest of these orbitals. So let's go down here. This is very similar to this one. It's not symmetric about inversion. So it's also a U. Let's check the Z rotation. So Z rotation would rotate this way. That would flip this over to there, that over to there. So that's anti-symmetric. So far we're looking at either a B2U or a B3U. Then when we look at C2 in the Y direction, that rotates this around to there, that around to there. That is symmetric. So now we're looking at B2U. So we can write down B2U here. Let's do this one next. This is symmetric about inversion. So because that would go there, this would go there, these two would switch with each other. So this is a Garrod representation. It is also in line with the Z coordinate axis, which generally means it could be a totally symmetric representation, but let's check. If we rotate about the Z direction, that's spinning it this way, that is symmetric. So we're either looking at a AG or a B1G. Now if we rotate in the Y direction, that rotates this around there and this around to here. That is symmetric. So now we've gotten it down to AG. These s orbitals down here are very similar. They are also totally symmetric. And so this is also an AG. But again, we could check. It's symmetric about rotation in this direction, in that direction, in this way. So it would be this way, that way, that way. It's symmetric about inversion. That's any of the reflection planes. So a reflection that way, a reflection plane this way, or the plane of the paper. Those are all symmetric. So AG for that. Now let's come up here. Now this is also symmetric about inversion. We could move that there, that there. That's symmetric. So we've got it down to some kind of Garrod representation because it does have inversion symmetry. Now let's do a rotation about the Z-axis. So that would flip this around this way. So this would go up there, that would come down there, these would flip. So that is anti-symmetric about the Z-axis. So now we've gotten it down to B2G and B3G. So if we look at a rotation about the Y, that would rotate this around. So that would move this here and that would go there. That is, let's see here. No, wait, that's an X rotation. Y rotation would rotate this way because Y is coming out of the paper. So that would be symmetric about that. I made a slight mistake there in how the Y rotation looks, but if I move this over to there, that's the same. That over to there, that's the same. So this should be B2G because it was anti-symmetric about the Z. There's a symmetric about the Y, and it's anti-symmetric about the X because the X's would move it over there and over there. So B2G. We can do the same thing with this one. This is also symmetric about inversion. We're just changing the plane about what it is. We can also use the reflection planes to figure this out. So let's try one where we use the reflection planes. XY plane is this one coming out of the board. And if we were to reflect about that, that would be anti-symmetric. Now if we choose the XZ plane, which is the one that cuts through the middle of these, that is also anti-symmetric because that would flip this to the back, that to the front. These would change their position. So that's anti-symmetric. So as we see here, we can look at the character table and see which ones we're matching up with. Looks like we're matching up with B3G, anti-symmetric about XY plane, XZ plane, and symmetric about the YZ plane, which is this reflection here. So that would just move this half up to the top and down. That's symmetric. So B3G. This is not symmetric about inversion because if we flipped that, that would go there. Those would change polarity. So this is an Untitled representation. Now we just need to match up with some reflection planes or rotations in this case. So let's look at the reflection plane. Let's try the XY plane, which is right in the middle. And if we reflected that, that would go there, and this would go back over there, and these would flip positions. That would not be symmetric about the XY plane. So right there, we've gotten it down to where it's B1U, because not inversion symmetry and not symmetric about the XY plane. Oh, I've got to go one more because it could be the AU symmetry. Let's try XZ plane. XZ plane is the plane of the board, and it is symmetric about that. And so we've eliminated the possibility that it could be AU because there's two other planes that it's symmetric about. So this is B1U. This is also a B1U symmetry down here. You can go through this operation to verify that, but we'll skip it for time at the moment. Now we need to look at what the carbon orbitals are, because right now we've just determined what the oxygen orbitals are. Now if we come over here, we can look at the chart and we can see which orbitals the carbon atoms have. So it's right here. These are carbon orbitals. So we have the 2s, we have 2pz, 2py, and 2px. S orbitals are a sphere, and they are totally symmetric representations. So they fit the AG symmetry. So they have AG. And then we could go through and draw out the orbitals for PZ, PY, and PX and find it out that way. Or we could just take advantage of the fact that these orbitals line up with the same symmetry as the coordinate axes do. So generally character tables will have the coordinate axes symmetry already noted in them, and I've done that over here. So we can simply write them down by noting that the Z coordinate axis has the same symmetry as B1U, and the Y has B2U, and the X has B3U. So we can simply write those down. B1U, B2U, and B3U. Now we have the symmetries of the carbon orbitals, and we have the symmetries that are possible out of the oxygen orbitals. From here, we can construct the molecular orbitals, but I'll do that in a later video.